important for you. The comment are the following. First comment. The constant C, C1, which is 3m plus 2m, is also known as bulk viscosity. Why bulk viscosity? Is a viscosity effect due to axial strain deformation of the velocity. Okay? Now, look at me. The viscosity dissipation for fluid typically are associated not to axial but to tangent motion. Not to the axial but to tangent. So this kind of contribution to the viscosity, we have these two characterization, the spheric and the deviatoric. This sphere here, C1, is practically zero, and this, the fact that the C1 constant B is practically zero, can be demonstrated in the theory of kinetic gas, for example. But is also demonstrated experimentally, well demonstrated. So if you assume this constraint, you have that 0 are equal to 3 lambda plus 2m, and so you have that the 2 lambda constant are not independent, but you can found one of this, for example, lambda, as equal to the other one by 2 by 3. Okay? At the end of the story, how many parameters are necessary for describing the viscosity of a Stoichiometric fluid? Practically one, not two. Note that for the elasticity of the solid, you have an identical procedure for describing the isotropicity in terms of elastic solid, but in that case, you have both the actors, both the characterizing parameters, one for spheric part and the other one for the deviatoric. So in that case, you have to keep both of the constant for describing this isotropicity. And for the elasticity of the solid, you have two constants, the Young modulus and the Poisson ratio, and so on, or the two elastic modulus, okay? But for the viscosity of the fluid, you have only one. Only for the viscosity of the fluid, of the Stoichiometric fluid, since the bulk viscosity is practically zero, you have only one parameter. Only one parameter is necessary for describing viscous behavior in Stoichiometric fluid. Stoichiometric isotropic fluid. Another point, another comment. This quantity V dot dot D. This quantity has to be greater or equal to 0 for any transformation, because this is a part of Clausius inequality. Okay? But if you decompose this in C1 spheric part plus C2 deviatoric part double inner product with ds plus ds. This is d, so you have to multiply by d s and excuse me. Excuse me. V is V. Non posso cancellare più. Ok. Okay. V is V spheric plus V deviatoric, and D is D spheric plus D deviatoric, okay? But V spheric is C1 D spheric. V deviatoric is C2 D deviatoric by D spheric plus D deviatoric. Okay? This is interesting. It's interesting because when you multiply a spheric part with a spheric part, you have C1 D. You have C1 D spheric dot dot D spheric, and you should have plus C2 D deviatoric dot D deviatoric, but you should have also the mixer term. But can be demonstrated that this mixed term, like C1 D spheric by D deviatoric, are equal to 0. Try to demonstrate this. And therefore, VDD, which is greater than 0 for all transformation, is equal to C1 ds square plus C2 d deviatoric square. Remember that this inner product is performed simply multiplying the corresponding term and then sum. Okay? So in the case of the same quantity, you have the square of the term. So you have positive quantity. And what does it imply? This has to be greater than 0 for any transformation, which means for any d. And so this implies that C1 has to be greater than 0 and C2 has to be greater than 0. And these are also known as the constraint on parameter characterizing the fluid in terms of thermodynamics. In other words, the thermodynamics, not aerodynamics, the thermodynamics, and in particular the Clausius inequality, is able to impose constraints on the parameter characterizing the viscosity of the fluid. Okay? This is something like to say that a damping coefficient is always positive if it is a damping coefficient. And this C1 and C2 are the rule of damping coefficient. Okay, I finished this part, and now I want to talk about New chapter, unsteady potential flow, uncompressible potential flow. Let me list our hypothesis of work. We want to consider uncompressible flow, and uncompressible flows means something. We want to consider unviscous flow, we want to consider initially irrotational flow, and we want also to consider adiabatic transformation. Okay, this is our physical hypothesis. Oh, another one important, I want to consider attached flow. We don't want something like this. No. Okay? Uncompressible flow. dr on dt are equal to 0. So, for any particle, the density keep constant and does not vary in time. Note that I'm imposing this on the material derivative or substantial derivative, not on the other one. Unviscous flow, V is equal to 0, identical equal to 0. And therefore, the stress tensor is equal to minus Pi. We have only reversible part for the stress tensor. Initially rotational flow. Initially means at initial time, what happens? At initial time, how do you indicate the vorticity? Which kind of letter? Zeta or omega? What about the majority? What about you on remote sensing? What's your preferred letter for vorticity, zeta or omega? Hello?
Omega for the angular velocity and zeta for vorticity.
So you are currently distinguishing symmetric and antisymmetric part. Best wish. Zeta. I prefer zeta. Okay, and zeta is for oh, excuse me. Zeta is a vector. This is the rotor of the velocity. And so rotor in English is rot of v. This is the symbol, and this function is a function of x and time, but we are at time equal to 0. So at the beginning, zeta is 0 at the beginning. And what does it mean? You are in the airport, the aircraft is at rest, everything is at rest. So V is 0, the rotor of V is 0 as well, 0 vorticity. Okay, adiabatic transformation, you have R theta ds in dt equal to divergence of Q minus plus V dot dot D, remember? And you have this 0 because the viscosity is 0. You have adiabatic transformation, so adiabatic means no motion, no head flux vector, and therefore you have an asentropic. The entropy is identically equal to 0. Okay? S is equal to 0. S of x anytime. So the energy equation is identically satisfied. The entropy is 0, that's all. So we don't need to consider this equation anymore. And the last equation is that the flow is attached. Okay, this is a preliminary. A preliminary of consequence for unsteady, uncompressible potential flow. Now, I want to work on this point, and what does it mean that at t equal to 0, we have zeta equal to 0. We have a list of facts to be considered. First of all, we can introduce another concept. We introduce the quantity gamma. Gamma is a scalar, which is currently the circulation, known as the circulation of velocity dot dx. When you have a fixed circuit of material particle, please, this definition is associated to a line, a closed line of material particle. So you have to fix a closed line of material particle like this. And at this time, these material particles are currently occupying a set of points, a physical point. And the red line is a picture of this point. Each of these points has a velocity. For example, this point has a fluid velocity like this other. The red line is arbitrary and is indicated like C. C is for contour. Okay, a contour. So here you have a velocity vector in the flow, another velocity here, another velocity here. Okay, nothing to do with tangent. No, because this line is arbitrary. I have drawn this line. So I may draw this line, and I may compute this quantity, just multiplying the velocity for an infinitesimal element dx like this, and then take the dot product with these two vectors, and sum. At the end of the story, you have gamma. Okay? Introduce this gamma, the circulation gamma. This is a scalar, because it's a sum of dot product. Second concept is the Stokes theorem. Stokes theorem states that if you have a contour like this, for example, and if you consider a surface having this contour like this, for example, I am not able to make a nice draw. You have to consider a surface, arbitrary surface, having that contour. How many surfaces you have with that contour? Many. If you fix your contour, this is important. You fix the contour. You may have many surfaces with that contour. Many surfaces made of particles, different particles. Okay, this is an important point for further discussion. The Stokes theorem states that if you consider one of these surfaces, and if you decide to have a verse of this circulation integral like this, for example, and if you fix on the surface a consistent direction of the normal, following, for example, the role of the right hand, in the sense that you have a circulation and you have a normal. You know the story, guys, because you studied Maxwell equation, okay? And you apply Stokes theorem together with Gauss theorem as well, okay? However, fix a consistent direction on the curve with the normal of the surface, for any normal of the surface, okay? If you fix consistently these two quantities, this is the normal, the surface at this point, like that, and this normal M, in this case, the normal is inside the curve. You have a normal and you have a direction following the rule of the right side. The Stokes theorem states that this circulation of the velocity is identically equal to the flux on the surface S. This is the surface S, having that circulation curve as contour, or the rotor of V, in other words, the vorticity zeta dot M in the S. Okay, so this is the Stokes theorem. What at the moment, fix these three facts. We have this, we have one, and we have two. And this is a third point as hypothesis. What I want to, you have these three elements, 1, 2, 3, okay? What I want to demonstrate by these three elements is the following. If the flow is irrotational at the beginning, then after 1, 2, and 3, it will be potential in any time. For any time greater than 0, zeta should be in any time equal to 0. But please underline this point, in almost all x. So we have to exclude some special point by this property. Okay, I want to stop here after the first hour, and in the second hour I will demonstrate this key point for understanding the steady and compressible flow, for understanding the unsteadiness of the flow. Okay? Okay. Yes, it's Greek zeta. Vedi vissuto quella stagione cinematografica depressiva, galoppante in cui c'erano minuti interi di silenzio con rumori di elettrodomestici, queste cose svedesi, invedibili, e questo proiettore mi dà, con questo silenzio mi dà questa idea. Sì. Naturalmente tutti coloro che sono a casa riescono a vivere in maniera molto più meno imbarazzante e disperata questi momenti. Certo, se fossero qui sarebbe molto meglio, ci divertiremmo un po' di più, però troppo non si può fare. Cos'è eccessivo? Non si sa che cosa è eccessivo oggi, non si sa.
No. Infatti alla fine penso che lui parla singolarmente, se non di lezione, perché parte che comunque essendo così si parla in casa a Roma.
Certo.
Allora, ok, però appunto per i ragazzi che o non hanno preso proprio una casa a Roma, oppure stesso i romani preferiscono non venire. Io mi sento un pochettino in obbligo numerato, quasi in obbligo numerato.
Ci devi rientrare con le spese, diciamo, come si dice a Roma. Certo, ma fai bene, certo, però devi essere molto prudente.
Sì, no. La motina, mi porta una scrivina.
Certo, detergente dove stava qui? Dovremmo averlo chiuso in cassaforte, perché noi qui il detergente ce l'abbiamo, ma chiuso in cassaforte.
No, vabbè, io.
No, vabbè, lo prendiamo.
No, dicevi pure c'è un
Lo so, però. Le tasse le paghiamo tutti, anch'io.
Ma poi io che ci sarà la possibilità di venire qui a lezioni all'università in presenza, però che comunque ho la macchina, cioè ho la fortuna di avere una macchina, e quindi non prendo i mezzi e posso venire. Però molti altri che magari non hanno diverse macchine in famiglia, non vogliono venire qua, non hanno
Certo.
mezzi.
Provate ad organizzarvi sempre in sicurezza anche tra di voi, se avete degli amici, magari in due in macchina si può affestare uno. Tanto c'è state in macchina, io lo vedo la sera in giro, quindi però insomma anche lì un po' di prudenza non sarebbe male. Ok. Yes, constant, but I am free to fix the constant to be equal to 0. Yes, of course. The entropy does not variate. This is the consequence. Apart issues concerning Krakow theorem, but we are not in compressible flow. Okay. Again, please, I want to focus now the discussion on this, on the issue on what happens to the fluid in time different by the initial time. Look, equal to 0, you have that zeta, Greek zeta, thank you, is 0, and using the Stokes theorem, you have that the integral of zeta dot n is equal to 0, and therefore if you have a circuit, if you have an arbitrary circuit like this, and you evaluate the circulation corresponding to this circuit, the circulation is v dot dx, and this is identically, this circulation is identically equal to the integral on the surface S. This surface is not directly, stress this point, is not directly corresponding to C. You may have many surfaces C, S, having C as a circuit, okay? However, take one of this. No. And you have that zeta dot n ds has to be 0 because this is 0 at this time. And so you have that the circulation is 0. If the circulation is 0, and it's always 0 because you can choose another circuit is always 0. And if you have 0, and if you fix this point here as A point, and this other point here as B point, you have that 0 is equal to the circulation v dot dx, and this is equal to the line integral on this region. Consider this region as AB, but AB in this path here, v dot dx plus the BA in this other path here. Okay? Therefore, by this, you have that the integral from A to B following the path this here, this is equal v dot dx is equal to minus the integral from B to A, and therefore plus the integral from A to B again, but following this path here. So I am saying that when you take the integral following this path, you have the same value when you take the integral following this path here. This is equal to this, but it should be equal to this, should be equal to this, and this, everything. And so forth. Therefore, you may define the function phi as a function of x such that be equal to the integral from a to x of, please attention, v of another, please use another letter indicating the position. For example, x bar vector dot dx bar vector. Okay, so you can define a single valued function, which is a function of the second edge of integration of this integral. So this function depends on x, and this is the x of the dependency. Is independent, and this function defined this way is therefore such that v is the gradient of such a function. And this is a so-called single valued function. In Italian funziona con un solo valore. But unfortunately, this is systematically, definitively true at initial time. And what about next time? And for t greater than 0, this is the point that probably you don't know by previous course. Okay?
Sorry, Professor.
Yeah?
May you turn on the recording, please?
Oh, excuse
Please.
me. Yeah.
Thanks.
Yeah. I'm sorry. Just to recap what we have done in this time, I have defined these scenarios for uncompressible, unsteady potential flow. These are the hypotheses. And now we are focusing in the initial time. And the initial time, we have that the vorticity is 0 by hypothesis. I want to consider this point, 0 vorticity at initial time, but I want also to introduce the as a further point, the circulation concept, and together the circulation, the Stokes theorem concept. Okay. However, if you have zeta equal to 0, you may define a velocity potential field. You may define the function velocity potential as a scalar function which is a function of this edge of integration x of the velocity, and this definition of single valued function is equivalent to say that the velocity here is the gradient of such a function. This is the direct and the inverse definition of phi, excuse me. This is true strictly for initial time. And what about the time greater than 0? Okay, for time greater than 0, we have to consider a last contribution. We have written 1, 2, 3 here, 1, 2, 3 here. I want to add 4. 4 point useful for our demonstration. The point is that if you consider a circulation scalar in a curve, and if you consider the development of this quantity, so you have to follow the particle in the motion, the derivative, the type derivative of this quantity is identical equal to 0. This is also known as do you know the name of this theorem?
Kelvin theorem.
Okay, Kelvin theorem. Okay, and this Kelvin theorem is essentially something related with momentum conservation. So let me list here your first principle. We have the mass conservation, here described by the derivative of the density with respect to the time plus rho, the divergence of the velocity, is equal to 0. This is the first one. The second one is this mass conservation, mass. And the second one is the momentum equation, also known as Cauchy momentum. In Italian, momentum is quantità di moto, non è il momento. And so we have that rho, the derivative of the velocity, is equal to the divergence of the stress tensor plus eventual per unit volume force, like rho F. And F is a force per unit mass, and rho is the density. So you here could include the presence of the gravity, for example. And you have also the angular momentum, but angular momentum conservation is the fact that T is symmetric. And finally, here you have the energy, but we have, we have the energy conservation, but we have used this energy conservation just now in the entropy form, ds on dt equal to 0 in our case. Okay. Now, this theorem is based on the this quantity is based on the momentum conservation. In fact, the demonstration of this is easy. Consider that the derivative with respect to t of gamma is equal to the derivative with respect to t of the circulation integral v dot dx. Okay? Now, when you have to derive an integral, you have no, it's not easy. It's not so easy. You have to consider two facts. The function to be integrated is varying in time, but also the motion is moving the body. You have to follow the body, and so your differential dx is actually varying in time as well. Okay? In the theory of double integral or triple integral, you moved from Cartesian coordinate to spheric coordinate or cylindrical coordinate for integrating function in a domain. And you know that your dx of elementary volume or elementary segment, elementary surface has to be variated whenever you change the coordinate. In that way, you are considering exactly this point. But in this case, it's very easy to consider this variation in time. Just consider this product, this as a product between two quantities depending on time. And therefore, this derivative is equal to the integral of c by the derivative of v with respect to the time. This is a total derivative, and so it's a substantial derivative for the particle. Dot dx plus the derivative of a product plus the circulation of v dot the derivative with respect to the time of the x vector. X is the motion. X is representing the position of the occupied by the particle in that time, and we are following the particle in this motion. Therefore, this is the motion, and the absolute derivative, time derivative of the motion is the velocity. So this quantity here is dv. Because by definition, the velocity is the derivative in time, the substantial derivative of absolute derivative of the position. So this quantity is equal to the integral of dv dt dot dx plus the integral of v dot dv. Okay? But this is equal to the differential of v dot v by 2. If you take the derivative of the square of this quantity, you have the derivative of v, the differential of v dot v by 2 plus the differential of v dot v by 2, a product. 2 times eliminated. This is the famous 2 of the kinetic energy. Ladies and gentlemen, what's the original 1/2 in kinetic energy is this. And so here this quantity is equal to the integral of the differential of the quantity v squared by 2, where v without any kind of underline or vector symbol is the magnitude of the velocity. Okay? And when you have a closed circle, you have to evaluate the magnitude of the velocity in a point minus the magnitude of the velocity in the same point. And if the velocity is a continuous function, this integral is identically equal to 0. Okay? Now, apply the momentum here, avoiding the buoyancy force, avoiding the force per unit mass here, the gravity. And so this derivative is equal to the divergence of t. But the divergence of t, what is the divergence of t? The hypothesis here is that t is reversible part only. So the divergence of t is identically equal to minus the gradient of t. Okay? Do I have to illustrate this point? Are you able to? Okay, advanced student. And so this quantity is minus, at the end of the story is minus, this is the comment for this part here. And here, we have all of this part, we have minus the derivative of the gradient of the pressure dot dx. And what is this? It's okay? No? It's not okay. Asterisk, gradient of p dot dx is equal to the derivative of p with respect to x1 dx1 plus the derivative of p with respect to x2 dx2 plus scalar product. Okay? The derivative of p with respect to x3 dot the x3. What is this? This is the development of the differential of p. And therefore, take this circle integral, and you have to, this quantity is equal to a value of the pressure in a point minus the value of the pressure at the same point. We should not have any kind of discontinuity for the pressure in subsonic flow, and therefore this is identical equal to 0. So we have demonstrated the Kelvin theorem. Note that, please understand this point, the validity of the Kelvin theory is based on the momentum equation. We have applied the momentum. We have substituted this. We have substituted this with this momentum application. This is momentum based. Okay? So we have 1, 2, 3, and 4. We have 1, 2, 3, 1, the definition of circulation, 2, Stokes theorem, 3, we are supposing that the vorticity is 0 at initial time, and 4, we have to consider the Kelvin theorem on a circulation. And now I have to tell you a tale like Boccaccio, like Gottfried Chaucer in the Middle Age. Okay, the tale is the following. Consider this body, and consider at initial time a contour like this. At initial time, zeta, where is it? At initial time, zeta is 0 by hypothesis. Okay? So at the initial time, you have that gamma at initial time for this contour, which is equal to the integral of zeta at initial time dot n. I'm using Stokes. I am using all the 4 recipes, all the 4 ingredients. Stokes is equal to this, and therefore is equal to 0. Okay, for applying Stokes theorem, I am fixing this C. I am considering all the possible surface, and we have always 0. Okay. Next, please. Now we want to apply this Stokes theorem. We have that the derivative of gamma has to be 0. And therefore, in this time, I have gamma 0 equal to 0. And next time, go ahead, in t equal to t1, what happens? Which is the mover of this development? Is the Kelvin theorem. In fact, at t equals t1, gamma in t1 is still equal to, for that contour, a fixed contour, we have fixed the contour of particle. Again, we have 0. So, in this time, in this red time, the contour is moved just here, and you have here gamma in T1. which is 0. Okay? Note that we are in a differential time, in different time. T1 is greater than 0, and we have just another picture of our movie, and then here we can, in this time, we can use the arbitrariness of the surface as associated to the contour. In fact, considering all the possible surface as having C as contour, comma, note we are calling the arbitrariness of this position, considering all the possible underline as surface. You can apply again Stokes theorem, and you have that gamma in T1 of the circuit is again 0 and is equal to zeta in the time T1 for x on the surface d dot n ds. So in the red position of the circuit in time T1, you have to state that for all this surface having this contour, this red contour, this integral has to be 0. And you can guarantee this only if the surface we are considering in this span, this variation, have all the vorticity in its point equal to 0 as well, because of this arbitrariness. Okay, so because the arbitrariness zeta x in T 1 has to be 0. Because of arbitrariness of S. Okay? This kind of demonstration is also known as by construction demonstration. I am building the solution of this theorem, the conclusion of this theorem. Next move up to here, look, green time. Green time. The green time is this. This is gamma C in time T2, the green time. Same kind of conclusion. Again, also in this case, the circulation composed by the same particle is still 0 as before. And this is because of the Kelvin theorem. And again, you can associate to this circulation by the Stokes theorem many surfaces having this circulation as contour, and all the points spanned by this surface are points with 0 vorticity, and blah blah and blah blah and blah blah. So I am spanning Remember also that we started, this is the point t equal t2, same conclusion. The same conclusion is that zeta, in any point spanned by the surface, comma, T2 is equal to 0. Okay, now, of course, we can go at limit, look at the limit, which is very interesting. The limit should be something like that. Gamma C in T3, and gamma is again equal to 0. And you can ensure that the vorticity in that time is 0, considering all the surface, blah, blah, blah. Having the blue contour as boundary. Let me do a comment. A comment here is that note that at time equal to 0, we may choose many contours. So to cover the initial space. And so we have the capability to discover. So we probably will discover that zeta of x in any time is equal to 0. Because of this double arbitrariness. The arbitrariness on choosing the initial contour, and the arbitrariness to consider all the surfaces having that contour as boundary. But are there points that have to be excluded by the statement zeta x t equal to 0? Are there, could be point with not 0 vorticity? Considering this mechanism. Well, if you consider this mechanism, here is the point. Here is your profile, and the points are the following. Let me use violet, and the points are the following. Look. This is the worst possible degeneration of our original circle, respecting all what I said to you. Which are the points that probably should be excluded? I think that the points that should be excluded are this point here. in 2D vision. In 3D vision, the point to be excluded should be this here. The geometric point these points are the point these are the point not are maybe the point positions of material particle leaving the trailing edge. So the flow is potential in other words zeta x t is equal to 0 for t greater than 0 in any time but in the point x wake defined as positions of the material particle of fluid, material particle of the fluid leaving the trailing edge. This kind of flow is also known as quasi potential flow in this sense. Why quasi? Because we are stating that exists a function of x and time such that v is equal to the gradient of v defined in any time in, look this vision in 2D, here the body, and this is the domain. This is the fluid domain. This is the fluid domain of potential flow. This is going to infinite. But this part here is part of the boundary domain. And this surface here is the wake surface as SW. W is for wake. Of course, this surface, the knowledge of such a boundary is part of the solution of the problem. This is the point. Is not the easy complication of the problem. The geometry of S wake, the geometry problem, in general, the position and geometry of S wake is part of the solution. Okay, so for example, if you have an airfoil or wing with an angle of attack, you know the story, the end of the story. So you have after the trailing edge, we are talking about unviscous flow, guys, unviscous. After the trailing edge, we may have a contact discontinuity, and that's the way. Contact discontinuity, but the flow is potential, just upper, just lower the contact discontinuity. As in gas dynamic, for a weak shock, the flow is potential upwind, the shock downwind, but in the shock line, you have a discontinuity of the normal velocity. It is not potential in the shock. So the shock in gas dynamic is part of the boundary of potential problem. And this is the same for unsteady, uncompressible potential flow. So the trick is the following. In a steady aerodynamic, the flow is again potential. And therefore, what about now? Just let me write the final equation. The final equation for potential flow is mass conservation, which means divergence of V equal to 0, which implies Laplacian of phi equal to 0. We have boundary condition on body, on infinite domain, and on wake. In fact, our boundary are body surface, are infinite surface, and are wake surface. We know the boundary condition on the body, yes. The impermeability condition. The normal component of the flow and dot flow velocity, which is the gradient of phi, is equal to the normal component of the body velocity and dot v body. Okay, this is the impermeability boundary condition. At infinity, you may impose, for example, potential equal to 0. You don't care. It's an essential constant, unperturbed flow. And what about the wake? What about the boundary condition in terms of potential? Boundary condition on the contact surface in terms of potential, we don't know. And this is the story in the next for the next lecture. I have a question for you, a final question. In this scheme of potential flow, are we respecting the momentum? This equation is a equation of mass conservation. And where is the momentum? Where is the momentum? Please tell me. The momentum was included in the application of Kelvin theorem. We use Kelvin theorem for demonstrating that the flow is potential in every time. Okay? So forget the idea that for potential flow, the momentum is not important. It's important. For guarantee the potential flow in any time. Okay? This is one of the master lesson of this course. Okay? Thank you. See you next week and have a good weekend for everybody.
Sorry, Professor.
Yeah?
A question about the momentum conservation. When we substitute the derivative of p, velocity, the density was
constant.
So
what kind of flow we have? What kind of flow we have? We have
incompressible.
We have a compressible flow. So here, yes, we have 1 over rho. I forget 1 over rho.
Okay,
yeah,
okay.
Thank you. But 1 over rho is out of the integral.
Perfect.
Okay, 1 over rho.
Thank you very much.
Okay. Ok.
Professore, scusi, invece da lunedì come ci si dovrà comportare nell'eventualità uno voglia venire in facoltà? Cioè è cambiato qualcosa con questo nuovo decreto regionale? No?
Niente. Poi andate avanti tranquilli. Affidiamoci alla governance.
Ma a quale? A quella dello Stato o a quello